Imagine this. You're standing at a real crossroads for your business, staring down a huge investment. We're talking, potentially tens, even hundreds of thousands of dollars. And if you make the wrong call, well, the fallout could seriously disrupt your whole operation. It hits your production, your part quality, and let's be real, it could absolutely wreck your budget. So today we're diving deep into exactly that challenge. We're focusing specifically on how you choose the right profile machining center. This isn't just about buying equipment. It's a strategic move that impacts your capabilities, your profitability, really for years to come. Okay, let's unpack this.
It really is amazing and honestly a bit concerning how often companies kind of trip up right here. They might just jump at the lowest price tag,
Yeah.
Or on the flip side, get dazzled by a machine with all sorts of bells and whistles they'll frankly never use. I remember this one client vividly, actually. They were so close to buying this absolute beast of a machine. Super powerful, built tough for steel work. But here's the thing they almost missed. Their entire business was machining long aluminum extrusions. If they'd bought that machine, oh boy, they'd have paid a massive premium for power they didn't need. And crucially, they would have lost out on the super high spindle speeds and the specific cooling you need for aluminum. For that smooth finish and getting chips out.
Yeah.
Luckily, we caught it in time, saved them potential fortune, and kept their quality from taking a nosedive.
Oh, yeah.
So our mission today, for you listening, is to help you navigate this, define exactly what you need, match those needs to the machine specs, think smart about automation, and really, really look at the long-term value, not just the upfront cost. The goal isn't finding the best machine overall, it's finding the perfectly matched machine for your work.
That story is more than just a warning, isn't it? It really highlights how easy it is to get sidetracked, even for experienced folks. Because here's the really interesting part, and you touched on it. Before you even glance at a machine spec sheet, before you even think about features, you've got to be crystal clear on what you need that machine to actually do. It all starts with you and your specific jobs.
Exactly, yeah.
Skipping that homework, it's like building without a plan. You're just asking for trouble. You could end up with something too weak for your materials, maybe too slow for your production goals, or heck, just too small for your biggest parts.
Yeah.
And then you're turning down good work or trying clumsy, expensive workarounds. So what are these core questions? What's the foundation?
Precisely. And this isn't just like a suggestion, it's essential. There are three main things you absolutely have to nail down first. Think of them as the pillars supporting your whole decision. First, and probably the biggest one, the material you cut. This isn't just a small detail, it shapes the whole machine design. I mean, a center built for aluminum is just a different animal than one for steel profiles.
Right.
Completely different.
Yeah.
For aluminum, you need that high-speed spindle. We're talking 18,000, maybe 24,000 RPM. That speed gives you a tiny chip load per tooth, stops material sticking, reduces heat, and gives you that almost mirror finish you want with minimal burrs. Plus, you need really effective coolant to wash those chips away. Aluminum chips can be sticky.
Right, they get everywhere.
Now switch gears to steel. Here it's about power. Brute force almost. You need high torque, maybe 10 to 30 kilowatts, but at lower speeds. Think 6,000 to 12,000 RPM. That power lets you push through the harder material without the spindle, getting bogged down, which would kill your surface finish and wear out your tools fast.
Okay, material first. Makes total sense. What's pillar number 2?
Second is part size and complexity. Are you mostly drilling simple holes? Or are your parts more complex, needing work on multiple sides, maybe tricky contours? A basic 3-axis machine. Great for simpler stuff. But if you're doing complex angles, undercuts, hitting multiple faces, you'll need 4-axis or even 5-axis capabilities.
And that avoids multiple setups, right? Saves time, improves accuracy.
Exactly. Fewer setups mean less handling, less chance for error, faster overall production. It's a huge win. And the third pillar, required precision. You need to be honest here. Is standard tolerance okay? Or do your parts need extreme accuracy? Like down to plus or minus 0.02 millimeters, maybe even tighter.
That's incredibly tight.
It is. And machines built for that kind of precision aren't just tweaked standard machines. They're engineered differently from the start. Think active thermal compensation to manage heat expansion, super rigid frames to kill vibration, high-res linear scales. Trying to push a standard machine to hit those tolerances, you'll just make scrap and pull your hair out.
Okay, so material, complexity and size, and precision. Those are the big three.
Yep. Get those right, and you're building on a solid foundation. You won't buy a sports car when you need a pickup truck, or vice versa.
That's a great way to put it. It really drives home that the best machine is the one that fits your reality. So, okay, you've done your homework. You know exactly what you need. Then you face the spec sheet. And let's admit it, those can look like, well, like a foreign language sometimes.
Yeah. They can be dense.
Just rows and rows of numbers, acronyms. It's easy to get lost. And focusing on the wrong numbers, maybe the biggest number you see, could lead you to buy something that looks great on paper, but just doesn't deliver on your shop floor, affecting your output, your quality, your profits.
That's a really common pitfall. People get overwhelmed by all the data. So what really defines what a machine can do? Its limits, its potential. We need to focus on sort of three key groups of parameters. Spindle speed and power, we touched on that. Axis configuration and how fast they move. And the machine's rigidity and its work envelope, how big it is. These are like the engine, the transmission, and the frame of the machine. They dictate what it can do, how fast, and how well.
Okay, let's break those down. Spindle speed and power again, but maybe more specifics.
Right. We said aluminum needs high RPM, steel needs torque and power. Think of the spindle as the absolute heart. For aluminum, that 18,000 to 24,000 RPM isn't just about going fast. It ensures you form chips correctly. You don't get that smearing effect that ruins the finish and gums up tools. For steel, that 1030 kilowatts of power at lower RPMs, that translates directly into the muscle needed for deep, heavy cuts. You remove material efficiently without chatter, without stressing the machine or the tool. It's, like you said, speed versus power.
Got it. Okay, next was axis and movement speed. We talked 4 or 5 axis complexity.
Yes, but let's talk about the speed of those axes moving when they're not cutting. The rapid traverse rates. Think maybe 60 meters per minute. And good acceleration, too. People often overlook this. This isn't about cutting faster metal. It's about cutting down the non-cutting time. The time spent moving the tool from one hole to the next, or back to the tool changer.
So for parts with lots of features, lots of little moves.
Exactly. For parts with hundreds of holes or lots of small pockets, those rapid moves shave off seconds each time. Over the whole part, that adds up huge. It can dramatically shorten your cycle times, particularly in aluminum work, where you might drill tons of holes along a long profile. That speed is a game changer for throughput. Now for steel, while speed is nice, often the sheer cutting force and stability needed mean rigidity becomes even more critical than top travel speed.
Which brings us to rigidity and the work envelope.
Precisely. You need a heavy, stable frame, period, especially for long cuts or deep cuts. Vibration is the absolute enemy of accuracy in tool life. And part of rigidity comes down to the guideways. You'll see different types. LM guideways, linear motion, use rolling elements. They're super low friction, great for high speeds, ideal for aluminum machines. Then you have box guideways. These are solid sliding surfaces, much better damping, much more rigid for heavy interrupting cuts like in steel. Maybe a bit slower on the rapids though.
Interesting trade-off there. LM for speed, box for heavy duty.
Generally, yeah. And then the work envelope itself, the travel distance, especially the x-axis for long profiles, it has to fit your longest parts comfortably. For aluminum, that might be 7, even 10 meters. And you always want a little extra room, right? For future jobs you haven't even quoted yet. If your machine's just slightly too small, you might have to turn down profitable work later. These specs aren't just numbers. They directly translate to what you can produce, how fast and how well, right there on your floor.
That's a great point about future-proofing the work envelope. And the distinction between cutting speed and movement speed is really useful. It's not just the headline number, but how the whole package fits your specific work. Okay, so you've figured out your needs, you've matched them to the core performance specs. What's next? How do you get the most out of that perfectly chosen machine? Because even the best machine can be, well, underutilized if it's stuck in old ways of working, like relying too much on manual operation for everything. Skilled operators are vital, no question. But pure manual work has limits, doesn't it? It's slower, can be inconsistent, prone to errors, especially on repetitive jobs, leads to variable cycle times, lower output, and higher labor costs eating into your margins. Which is why automation isn't really a luxury anymore, is it? For many, it's essential.
You've hit the nail on the head. It's less if you automate and more how and how much.
Right.
Automation, and especially intelligent controls, they just amplify everything. Productivity, consistency, reliability, these aren't just nice to haves. They can fundamentally change your workflow. Think about automation examples. Even the basic automatic tool changer, the ATC, that was revolutionary. Eliminated huge chunks of downtime.
Absolutely. Can't imagine working without one now.
Right. But modern stuff goes way beyond that. Think automatic exchange tables. These let your operator set up the next job on one pallet while the machine is cutting on another. That can slash your non-cutting time by, say, up to 30%. Keeps the spindle turning almost constantly.
Wow, 30% is huge.
It is. And for real lights-out operation, you've got robotic loading, unloading. Let the machine run itself overnight. Huge capacity boost. Some even have vision systems now to check part loading, adjust the program automatically, less manual error. Then you get into intelligent controls. This is where the machine gets smart. They can monitor the cutting load constantly, in real time. If a tool starts getting dull or hits a hard spot, the control can automatically back off the feed rate, maybe adjust speed to prevent breaking the tool. That saves the tool cost, sure, but more importantly, it avoids unplanned downtime.
That sounds incredibly useful, almost like having an expert watching over it constantly.
Kind of, yeah. And these systems can also optimize cycle times on the fly. By constantly tweaking parameters, they might improve throughput by 15, even 25%, just by being smarter. And the ultimate, predictive maintenance. The machine analyzes its own data, flags a potential component failure before it happens, so you schedule maintenance proactively instead of dealing with a costly emergency breakdown. It's really amazing how these things turn the machine from just a tool into like a self-managing production system, efficient, reliable.
That leap from manual to intelligent is just staggering. The machine becomes less of a tool, more of a partner almost. But all this amazing tech, this precision, it comes at a cost, right?
Which brings us to that often uncomfortable part of the conversation, the price tag. It is just so tempting to look at the machine with the lowest initial cost, the one that seems okay on paper and doesn't break the bank up front.
Yeah.
But let's unpack that, because that low price can hide a boatload of expensive problems down the line, can it?
Oh, absolutely. It's a classic trap.
Things like frequent breakdowns, high maintenance bills, maybe terrible support when you need it, or just a machine that never quite performs as expected. Any of that can cost way more in lost production and pure frustration than you ever saved up front.
Exactly right. You absolutely have to look beyond that initial number, which, yeah, can range hugely, maybe $20,000 for something basic, up to $120,000 or even more for a complex automated setup. The key concepts here are total cost of ownership, TCO, and return on investment, ROI, over the long haul. Remember, you're not buying this machine for just the next few months. You're likely investing for 10, 15 years, maybe longer.
That's a long time. You need it to keep performing.
You do. And think about it. A higher quality machine from a reputable brand. Yes, it might cost more initially, but it will almost certainly be more reliable. It'll likely use less energy. It'll need less maintenance. Over a decade, add up the savings from avoided downtime, fewer repairs, lower energy bills, maybe even longer tool life because the machine runs smoother. Those savings can easily outweigh a higher purchase price.
That makes sense. The hidden costs of the cheaper machine add up.
They really do. Think about uptime. A machine that runs 95% of the time versus one that only manages 85%. Over 5 years, that reliable machine could generate 20–30% more profit, easily justifying a higher initial cost. Plus, you have ongoing operating costs, energy, tooling, labor. An efficient, automated machine lowers your cost per finished part. That goes straight to your bottom line. And one thing you cannot put a price on easily, support. When, not if, but when something goes wrong, having fast expert support from the manufacturer or dealer, that's priceless. It means getting back online quickly, minimizing that profit-killing downtime. So, at the end of the day, long-term reliability and efficiency, that's the real measure of value.
That's such a crucial perspective. The sticker price is just page one of a very long financial story. It sounds like TCO isn't just math. It's about valuing reliability and avoiding the cost of things going wrong. So what does all this boil down to for you, the listener, thinking about this big investment? It means picking the right profile machining center isn't about luck or being impressed by features. It needs a really rigorous look at your specific needs, a solid understanding of the machine's real capabilities, a strategic view of how automation can boost your output, and, maybe most critically, a clear assessment of its total value over time, not just the initial price. Make that informed choice, and you're not just buying metal, you're investing in years of efficient, profitable production for your business.
And thinking about that long term, it brings up a really interesting final question, doesn't it? As technology, materials, market demands keep changing so fast, what forward-thinking features, what kind of adaptability should you be prioritizing now in your next machine to make sure it stays perfectly matched and truly future-proof for that entire 10 or 15-year lifespan, not just for today's work? Thinking beyond right now, that's where the real long-term strategic value lies.